Good afternoon, everybody. Nice to see you. Pleasure to have this in-person event. So today we will have the presentation of Joaquin Medina Dueñas. Joaquin just joined the group 10 days ago. He's here, and previously was studying at the University of Chile. Under the supervision of, he made his master degree under the supervision of Luis Torres, that I think everybody knows. And we are lucky because he was very productive during his master, and so he will present us two stories about interplay between topology and bosonic excitations. I'd like also to say that Joaquin is very happy because it's the first time that he can present his work in person with real people and not online virtually, because he was completely hit by the pandemic. So I'm sure that will be, it's the first time. So yeah. Be relaxed, take it easy, take your time, and we will enjoy the talk. Thank you.
Thank you very much, Stephan. I'm gonna share my screen for the Zoom audience. Okay. And this works. So thank you for the introduction, Stephan. For those who don't know me, like Stephan said, I'm Joaquin Medina Dueñas. I come from Chile, where I finished my master's degree during last year. And this presentation is going to be about the work that I developed during my master's degree. So I work at the theoretical and computational nanoscience group since the Monday from the previous week. So the work developed during my master's degree gave birth to two different scientific articles. So dealing with pretty much different topics, but what groups them is the interplay between topological phases of matter and bosonic excitations. So we are going to work within the frameworks of state physics and quantum optics as well. We're going to deal with the behavior of particles such as electrons, phonons, and photons in two-dimensional systems and one-dimensional systems. Part one of this presentation is going to be about the article Co-propagating edge states produced by the interaction between electrons and chiral photons in two-dimensional materials, where we look at the interplay between electrons and phonons in a two-dimensional solid-state system. And on part two, we will focus on an optic system where we study the quadrature protection of squeeze states in a one-dimensional photonic topological insulator. We start with part one. So, why do we want to study the interplay between electrons and chiral phonons? Well, electron-phonons interactions are pretty ubiquitous in solid-state physics. Interestingly, from conducting polymers to superconductivity. And interestingly, recently there have been proposed, energy gaps, edge states, and even topological phases that emerge from electron-phonons interactions. We also know that breaking time reversal symmetry in a system may lead to pretty well-known topological phases, such as the Haldane model, for example, and more of our interest, topological Fouquet topological insulators, where the interaction between a hexagonal lattice and circularly polarized light gives birth to out-of-equilibrium topological phases. And when we started this investigation around 2019, 2020, recently, at the time, there was an observation, the first observation of chiral phonons, which was in tungsten diselenide, which brings a lot more focus to this interplay between electrons and chiral phonons. So, how do we obtain chiral phonons in a hexagonal lattice? Well, this is the phonon band structure for a hexagonal lattice with broken inversion symmetry, which allows to lift the degeneracy here between two chiral modes. So for a phonon mode, such as the one highlighted here in green, the eigenstate of the phonon mode, we can express it as a sublattice A part and a sublattice B part, where each part will have a determined circular polarization, left or right, given by the color scale here. So this circular polarization of each sublattice reflects a circular movement of the sites. So there's a term in the phonon chirality, which is intracell and is given by the eigenstates and by the circular movement of the sites. But there's also an intercell term, which is related with the phase difference of the movement in different unit cells. Because the phonon mode highlighted here has a non-zero momentum, it corresponds to value k plus as indicated by the band structure. Because of its non-zero momentum, the movement of the sites at different unit cells is different. So this site is at that point of the movement indicated by the starting point of the arrows, but a unit cell, neighboring unit cell is at a different part of the movement. See? So for a phonon mode in value k plus, we have a threefold periodicity. So if we translate 3 unit vectors, we're going to obtain again the same circular movement. Now, how do we couple the electron behavior to the chiral phonons? The basic Hamiltonian model is as follows. First, we will only consider one phonon mode with a given frequency and a given momentum. We consider the one highlighted previously with the circular movement of the lattice and with momentum corresponding to value k plus. The basic Hamiltonian model can be expressed in 3 terms. First of all, let's consider that the Hilbert space of this system is composed by the Hilbert space of the electronic part and the Hilbert space of the phonon part. It's Fock space. So the first term is a purely electronic Hamiltonian, where it has the term of the electronic Hamiltonian, the electronic description for a hexagonal lattice that we all know with its Dirac points and whatnot, and an identity in the phonon subspace. The phononic term is an identity in the electronic subspace and the free field contribution in the phonon space. So these 2 terms are diagonal in the phonon Fock space because one is proportional to the identity and one to the free field Hamiltonian. We can expand this Hamiltonian in the phonon Fock space and obtain something what is written here. So the electronic and the phononic parts are diagonal here, and we can view these 2 terms as an infinite series, as a semi-infinite series of electronic models, one stacked over the other with a difference of energy of h bar omega. The electron-phonon interaction Hamiltonian is not diagonal in the phonon Fock space and thus represents interactions between the different replicas that we have stacked. We obtain the electron-phonon interaction by a renormalization of the Baire hopping amplitudes considering the circular movement of the lattice that is given here. Okay? So with this electron-phonon interaction model, we start computing some band structures and density of states and stuff like that. So let's start from the picture where we have this infinite stack of electronic systems, one over the other with a difference of energy h bar omega. So as shown in the panels on the left, each replica has their own Dirac cones, and with no interactions, the band structure would look like this, truncated to only 2 replicas to keep the plot, readable. Once we turn on the electron-phonon interaction, an electron with a momentum corresponding to value k minus in the phonon Fock space of 0 phonons can absorb a phonon and thus scatters its momentum to value k plus. So the phonon non-zero momentum generates transitions between electrons in value k minus of the 0 phonon replica with electrons in value k plus of the 1 phonon replica. So with this, we see that a value selective pseudogap emerges. Why is it a pseudogap? Because the other values, value k minus in the replica 0 and value k plus in replica 1, are not connected by the adequate phonon momentum. So no gap is open between them. We can observe this in panel C, where replica 0 in black has a gap here in value k minus with replica 1 in red with value k plus, but the other values are not gapped. So we observe the emergence of a pseudogap, a value selective pseudogap, due to breaking of time reversal symmetry due to our chiral phonons. So is this pseudogap, or is this gap bridged by some topological edge states or something like that? To this purpose, we compute the local density of states of a semi-infinite ribbon. So in panel A, we have the local density of states at the edges of the semi-infinite ribbon, and we observe these 2 cones that are the background bulk states of the non-gapped values. We also observe these 2 truncated cones that are the gapped values. And bridging this pseudogap that we observe are 2 co-propagating edge states. And this is radically different from what is found in topological systems, where edge states are usually chiral or helical. So these two co-propagating edge states are due to a hybridization between the flat bands of the two different replicas. So replica 0 has its hexagonal lattice flat bands, and here they hybridize with the flat bands of replica 1. Okay, we can compute the band structure for a finite ribbon and project the eigenstate of these co-propagating edge states, and observe that the co-propagating edge states actually live in valley k minus of replica 0 and valley k minus of replica 1, and they are localized at opposite borders of the ribbon. So they are co-propagating along opposite edges. Okay. Now, what are the consequences of these co-propagating edge states on quantum transport within this ribbon? Oh, by the way, I forgot to mention this is a zigzag nanoribbon. We get different results depending on the termination. Okay, so what are the effects of the edge states on quantum transport? We imagine a setup where we have a zigzag nanoribbon and a zigzag nanoribbon with two transversal sections, left and right. Left for your point of view and right. So we compute the transmittance when injecting one electron along one of these transversal layers, the transmittance towards the opposite layer, and computed according to the transverse position. So those are the plots shown here in this figure. We do that for a pristine ribbon and for a disordered ribbon where disorder is 10% vacancies. We observe, first of all, that there's a strong directional asymmetry due to the co-propagating edge states. Transport on the left to right direction is strongly suppressed, while transport in the right to left direction is not. Also, for transport in the right to left direction, we observe that the transmittance is strongly focused at the same edge that was the input. So if we input a phonon at the left edge, I mean at this edge, it will transport along the same edge, and the transmittance is strongly focused here. When introducing disorder, we observe that the directional asymmetry is strongly robust, even in this case where we have point-like disorder, which should mix processes at all momentums. But we observe that the asymmetry is still strongly robust. So finally, we compute this system for the numbers adequate for graphene on hexagonal boron nitride and obtain favorable numbers. Hexagonal boron nitride will break inversion symmetry, which was necessary for obtaining chiral phonons. And for this system, if we assume an electron phonon coupling of 2 over 10,000 times the Baire hopping, we obtain a pseudogap of 4.5 millielectron volt, which is an experimentally accessible gap. So finally, in order to obtain this coupling between electrons and a specific phonon mode, we propose that this phonon mode should be excited, for example, by optical pumping, which was also the technique used for the detection of chiral phonons in tungsten diselenide. So, as a conclusion, what did we do? We studied the electronic properties of a two-dimensional material with interaction between electrons and chiral phonons. And by this, we introduce a novel time reversal symmetry breaking term. We found a rich phenomenology derived from the combination of inelastic processes and momentum transfer, mediated by the electron-phonons interaction. This results in the emergence of a valley-selective pseudogap with co-propagating edge states and that coexist with a continuum. And finally, in order to wrap up the idea of topology, this work, the reason why we investigated on the interaction between electrons and chiral phonons was motivated by searching for topological phenomena. However, we were not able to really characterize the resulting topological phase that we possibly could have found. We couldn't determine if these edge states are actually topologically protected or not. But it was the motivation that led us to all this work. With this, I conclude with the first part of the presentation. Yeah. Yeah. Yeah, sure. It could be a good time for questions, since now I'm going to pass to a drastically different topic.
So I can ask a question then. So the chiral phonons is really only related to the hexagonal symmetry, right?
Well, you could get chiral phonons in different forms of lattices. but we worked specifically on the hexagonal lattice.
In your case, so when you have edges or when you put vacancies, you break the symmetries of the system. But so I understand that you have neglected the fact that this symmetry breaking real space effects. We modify in any way the phonon vibrational density of state and properties. They are completely regarded as phonon, right?
That is so completely correct.
How can you? What is the argument to say that they will be perturbative on top of the in the flow case? Is there any argument or is there a way to say, okay, that will not kill my chiral phonons coupled with electrons when I put 10% vacancy?
Yes, yeah, you're correct. We assume that the vacancies do not break, do not bother the chiral phonons that we found for the pristine lattice. Perhaps one argument to claim that the vacancies do bother the electronic properties but not the phonon modes could be that the phonon modes have typically higher frequencies, so electrons should suffer their higher energies.
But I also consider it's optic modes because the energy of these modes are like high, right? Of these chiral modes.
Of the phonons,
yeah.
It's 150 to 100 milli-electron volts.
High energy. So I mean that they correspond to. I mean, I don't know if you will state what does that mean. You show some kind of like kind of circular. Circular vibration, right?
Yeah. This.
So this is really local scale. So if you get one of the atom out and you make a vacancy, you perturb quite significantly the modes. Right?
Yes. So you could do it, but we did not investigate on how the phonon modes are affected by including vacancies. For all this work, we assumed that the phonon modes remain unperturbed.
Completely okay. But I like it. Oh, sorry. You have to. Yeah, I don't know if there's any questions. Yeah, I see questions here. You have to use this.
I have to use this. Sorry. Okay. I mean, I understand that you, in your model, you consider a single chiral phonon. And it seems to me that you have assumed it's indestructible from what you say. So scattering with defects, etc., will not alter it. And all what we know from phonons, depending on the temperature, is that they scatter even among themselves. So how much do you expect to change the picture if you include two chiral phonons?
Well, if we include the two, right here, I don't know where the mouse is, there it is. Okay, so if we have this one and the other one in value k minus, those could cancel out, for example. Because the one in k minus corresponds to a time reversed case of the one in k plus, or for example, inversion symmetry breaking is needed in order to lift the degeneracy over here at the valleys. Because once we do have a degeneracy, the chiral phonon modes in the degenerate subspace lead to non-chiral phonon modes. So depending on the characteristics of the second phonon mode we have interacting, it could break our entire system and we obtain absolutely nothing interesting. And that's why it is important to propose, or at least think of a form that we could excite in particular the chiral phonon that we are interested in. And this would be by some optical pumping with a circularly polarized light with the adequate energy, which is the technique used to detect the chiral phonons in tungsten diselenide, because you generate a high population on them. Of course, experimentally there would be a lot of challenges, but it's important to think of a way one could do that.
Yeah, because and then the coupling, so can you show the slide where you have electron transport? Yeah, this one. Electron transport, yeah. So here you have a bias to drive the electron flow, but the bias is low, and you say that you assume that the phonons will be excited by light, and then you look at all these electron phonon coupling we suppress, or or we create these co-propagating edge states, which are kind of combination. It's like a delocalized polaron somehow, because it moves thanks also to the phonons, or it can move, or it's just like a renormalization of the electron velocity. Yeah, I missed if this is just a renormalization of the electron velocity due to the electron phonon coupling, or if it's something else. If it's something that exists because of the coupling and it's non-perturbative.
We include the interactions in a non-perturbative form, because
this I understand. But
where we put the model, we don't.
It's non-perturbative. But do you think the result could be obtained by treating electron phonon coupling perturbatively or not?
You think that?
Because the phonon energy is very high, but so electron phonon coupling should be quite significant. But
we did not investigate on that, but I wouldn't guess an answer. I'm not going to make an irresponsible guess.
That's okay. So I think we can come to the second part. Thank you, Joaquin. Let's move to the second part.
Okay. So moving on to the second part of this presentation, which is already the other way around, because this was the first part of my written thesis. But anyways, this is titled Quadrature Protection of Squeeze States in a One-Dimensional Photonic Topological Insulator. And here we aim to determine how does the topology of a photonic lattice interplay with the quantum properties of light, in particular squeezed states. So here we will start from the basis that we have in our hands, this wasn't experimental, but just to make the picture, we have in our hands a photonic lattice with topological properties. How is this? Well, topological physics is originally discovered and proposed for electrons in solid state systems, but topological physics is actually a fundamental wave phenomena, and we can extend it to photonics, phononics, spintronics, and many other stuff. So we can emulate the behavior of a spinless quantum particle with a photonic system by a waveguide array. How is this? Let's imagine we have a tight binding model given by this diagram over here, where we have the different sites, and the sites are connected by some coupling. So this is the tight binding model with topological properties that we wish to emulate photonically. We can do this with waveguide arrays, where each of the sites is composed of one waveguide, which extends along a third axis that enters the screen or gets out of the screen, however you want to see it. And that is the propagation axis. Okay, so each site is a waveguide array, is a single waveguide along which light prefers to propagate, and the coupling between different sites is due to the evanescent coupling of the bare waveguide modes. So if we put two waveguides very near to each other, they will have a strong overlap, which generates a coupling between them. And if we drift the waveguides apart, we will have a smaller overlap and therefore a smaller hopping. We may simulate the behavior of a spinless quantum transport by generating waveguides modulating the refractive index of an optic media. Here, the propagation axis Z takes the role of time, because the electric field, the electromagnetic field, evolves in Z as a quantum particle evolves in time. So we're particularly interested in the SSH system, which is the system we took to make our investigation. So the SSH system is a dimerized linear chain, where it has an intracell hopping U and an intercell hopping V, and all of the on-site terms are equal. So in the plot on the left here is shown the energy spectrum of a finite SSH system for different U over V ratios. And we observe that for U smaller than V, two edge states appear here with an eigenvalue pinned at 0. These edge states are topologically protected and are characterized by the Zach phase, which presents a phase transition at U equals V. And the edge states are robust against hopping disorder, which preserves chiral symmetry of the SSH lattice, and are fragile against on-site disorder, which breaks the symmetry. So here on the right is the eigenvalue of the edge states when we introduce different forms of disorder. When introducing hopping disorder, we can even get to very high values of disorder, and the energy is perfectly pinned at 0. However, when introducing on-site disorder, the energy of the edge state fluctuates. I mentioned that in this context of waveguide arrays, the energy of a state is also called its propagation constant, because it's the phase that it acquires along the propagation. So, a brief overview of the SSH system, which I assume is familiar. So now let's go to an introduction to squeeze state of light, which perhaps requires a little bit more detail. So, we will start from the description of a single mode of the electromagnetic field by the bosonic operator A. So, from this bosonic operator, we can find the quadratures x1 and x2 as shown by these formulas, and these correspond to optic, adimensional, position, and momentum operators in an analogy with what occurs for a quantum mechanical harmonic oscillator. Now, these quadrature operators have their own Heisenberg uncertainty principle, and from here we can define what is a squeeze state as a state that has reduced uncertainty in some quadrature, which can be x1, x2, or some rotated quadrature in phase space. So, a state which has an uncertainty lower to that of vacuum, which is equal to 1/4, that is a squeeze state and is a quantum state of light. So the phase space representation, or the Wigner function of this squeeze state is seen as an ellipse, because along one axis, along the squeezed quadrature, the probability of finding the state in that quadrature is squeezed, low variance, and because of the uncertainty principle, it is expanded in the orthogonal axis, so it is an ellipse and it is rotated according to the phase of the squeezing. This is for one mode of the field, but we may also define a two-mode squeeze state, which is, so we define the two-mode quadrature, which is a coherent superposition of the single-mode quadratures, and we may define a two-mode squeeze state whose phase space representation, its Wigner function, in the limit of infinite squeezing, tends to this expression right here, the two deltas, a perfect correlation between the positions and the momentums. And this is an optic version of the Einstein-Podolsky-Rosen state. So two-mode squeeze states are entangled states and are actually correspond to the paradigmatic EPR states. Now, straight to our investigation. The question we ask ourselves is, when propagating squeeze states through a photonic lattice, what is the effect of the lattice's topology on quantum properties of light? In order to determine the effect of the topology, we investigate the behavior of a topological SSH system and a trivial system, which is a linear chain with an on-site impurity, which generates a trivial edge state. We compare these two systems and introduce symmetry preserving and symmetry breaking forms of disorder, hopping and on-site. And finally, we ask ourselves, how can we harness the topological protection of quantum light? And for this, we simulate a quantum teleportation protocol that is topologically protected. So we start with the behavior of single mode squeezing propagating along this topological SSH photonic lattice. So we have a finite SSH system of 15 waveguides overall and some propagation distance. At the beginning of the system, at z equals 0, we inject a single mode squeeze state, which may be generated externally, and we inject it to a system and see how it evolves. And we focus on the squeezing along waveguide 0. So I mentioned as well that squeezing is measured by the standard decibel formula, where if we have squeezing, the variance in the quadrature will be smaller than the variance of vacuum, and squeezing is therefore a negative measure due to this formula. We can measure squeezing at a given quadrature with some rotation angle phi, or we can minimize this expression and obtain maximal squeezing at the maximally squeezed quadrature. So these plots over here show the squeezing along the propagation axis z, and all the plots on the right show different stuff that I'm going to tell you right now. So on the left, we have the squeezing, the evolution of squeezing for the pristine systems, the hopping disorder, and the on-site disordered. All blue curves correspond to a topological system, while all the red curves correspond to a trivial system, and the solid curves correspond to maximal squeezing, while the dashed curves correspond to squeezing at the horizontal and vertical quadratures. For all the systems, the initial state is the one highlighted here in light blue. Is a squeeze state, a single mode squeeze state, squeezed along the horizontal quadrature. So its Wigner function looks like this. We will work in a rotator frame where squeezing along all the pristine lattices is always in the horizontal quadrature, and at this point of studying the pristine systems, we observe no difference between trivial and topological lattices. We will have to include hopping disorder in order to see how the topology affects quantum properties of light. So panel C, highlighted in light blue, is the Wigner function of the hopping disorder topological system at some point of the propagation. I mentioned as well that we did about 100 random realizations of these systems with random disorder. So this is the Wigner function of one of the random realizations. This system presents a non-zero squeezing because the Wigner function does look like an ellipse. It is squeezed, and it is squeezed along the horizontal axis as well. This is true for all the random realizations that we performed. Therefore, when taken in an average over all the random realizations, squeezing at the horizontal quadrature is preserved. Squeezing doesn't rotate because when introducing hopping disorder, the eigenvalue of the edge states remains perfectly zero, as I showed you before. The scenario is different for the trivial system. Panels E and F are the Wigner function of two different random realizations at some point of the propagation. So we see that both of them are squeezed because both are ellipses, but they are squeezed in different quadratures. The rotations are different, and the rotations are randomized due to the randomization of the trivial edge state's eigenvalue. So when taking an average over all random realizations, we are taking an average over incoherently orientated ellipses, and thus squeezing is lost. When introducing on-site disorder, the topological system ceases to be topologically protected and behaves just like the trivial system. So on these terms, we conclude that topological protection of the propagation constant or eigenvalue of the topological edge state allows to preserve the phase of the squeezing. We study as well what happens with two-mode squeezing, and the results are pretty much similar. Now we consider two different SSH lattice and two-mode squeezing between the two edge waveguides. The results are pretty much the same, but what is interesting now is that we can talk about entanglement. The magnitude of entanglement is proportional to the magnitude of squeezing, not to its phase, just the magnitude. Thus, the magnitude of entanglement does not distinguish between a topological or a trivial system. However, the entangled variables between the system, position with momentum, whatnot, the entangled variables do respond to the phase of the squeezing. Thus, topological protection locks the entangled variables in this system. So finally, we ask ourselves, how can we harness this topological protection? And for this, we perform a quantum teleportation protocol. The purpose is as follows. We have an input state, which we want to teleport from Alice's location towards Bob's location. And for that, we have an output state, which should be as similar as possible to the input state. Alice and Bob share an entangled state, so Alice interferes her fraction of the entangled state with the input state. At the output of this interference, Alice detects the quadrature. So the act of measurement makes Bob's fraction of the entangled mode to collapse. Bob's mode collapses to something similar to the input state plus some phase displacement. So Alice tells Bob, she writes on her notebook and says, Bob, this is what I measured. With that information, Bob corrects the phase displacement and we obtain the output state. How do we incorporate topology to this teleportation protocol? The entangled state between Alice and Bob is a two-mode squeeze state, as the one I mentioned before, and we picture that it is created in some laboratory and it is sent to Alice and Bob by some topological lattices. The results of the teleportation are as follows. The input state we consider as a single photon state, and we perform the teleportation for topological and trivial systems, pristine and with hopping disorder. For the pristine systems, the output fidelities are pretty much the same, as shown in panels B and D. But when introducing hopping disorder, the topological system remains perfectly robust to hopping disorder. The fidelity is just the same as for the pristine system. However, for the trivial system, the fidelity is highly reduced. And something interesting here is that the output Wigner function does not present negative values. Thus, the quantum information of the input single photon state is lost due to disorder in the trivial system. This is because this protocol relies heavily on Alice measuring the maximally entangled quadratures with Bob. That is what makes Bob's mode collapse to the state that we desire. So when the entangled variables are randomized in the trivial system, the teleportation gets severely deteriorated. So we studied the quantum properties of squeezed light when propagating through a photonic topological lattice, focusing on the role played by the lattice's topology, and we found that the lattice's topology allows to preserve the phase of the squeezing. And finally, we showed how this topological protection can be harnessed for applications in quantum information processing. So this is what went into my master's thesis, but now I want to mention one other part that is work that I've been doing and that was ongoing in Chile before I came here. Not so much right now because we're on vacation, it's February in Chile, but this was ongoing, had promising results. So this is quantum interference of topological states in 2 dimensions. For this, I consider a waveguide array realizing the Haldane model, which may be realized by a hexagonal waveguide array with helical modulation of the waveguides along the propagation axis. This emulates a flow K topological insulator. This system is, we consider a sand clock geometry, what I call a sand clock geometry of this system, which is indicated by the figure on the bottom. So this system presents the Haldane model's chiral edge states that go in this counterclockwise sense. So we have 2 input states that goes toward this sort of quantum dot that is located at the waist of the sand clock geometry. An input states from the bottom left and an input states from the top right, and 2 output states from the bottom right and top left. So we can generate quantum interference between topologically protected states. And for this system, I have successfully performed simulations of the Hongo-Mandel effect. What is the Hongo-Mandel effect? The input is 1 photon at each input. So we have 1 photon here, 1 photon here, and the output is either 2 photons on one output, 2 photons here, or 2 photons on the other output. So this is measured by the 2-particle correlation functions between the different inputs and output. We see on the plot right here that for the input, indicated by this dashed green light, there's 1 photon at bottom left and 1 top right. However, at the output, there is no possibility, no probability of having 1 photon at bottom right and 1 photon at top left. Either they are both at top left or both at bottom right. So the output of this system is a Null state. I have successfully performed simulations on the system for the Hongo-Mandel dip and have proved that it is resilient to disorder. And with that, I finish my presentation. I want to say thanks to my master's thesis professors, Luis and Carla, and other collaborators during this works, Hernan and Gabriel. So thank you very much for your attention, and hopefully there are some questions or comments.
Topological photons and connection with entanglement. So, I don't know, more questions from here?
Any questions on the second part? Because the first one we already covered.
So, yeah, it's, but I don't really, so the last slide was a bit complicated to follow because, but let's come back to the first part. So the first part, at some point, you don't just have the SSH model, but you have a kind of lattices, right? When you look at the
the pointer stopped working. So
yeah, no, before, after. Yes, this one. We have waveguides and 0 to 14. So this is what? This is an extended system in 2D.
This is
it's just like
okay. So
no,
the z-axis is time.
The,
it's 1D, but the z-axis is time. So in a condensed matter version, we would have only a chain, an SSH chain. Okay. But we need the extra axis along which light can evolve.
But if the topological edge state, I mean, I didn't get it. They are squeezed quantum of light, but they are initially at the edges, and then they propagate it.
Yes,
it's just the way they change in time, being localized, and just all their localization.
So
properties modified.
We picture that the squeeze state is generated with some lasers, some artifacts over there, and we point the laser towards this point right here, the start of the evolution and the edge waveguide. part of the excitation couples to the edge state and remains localized at waveguide 0, and all this propagates towards the right. So part of the excitation remains localized at waveguide 0, but there's not a perfect overlap between the edge waveguide and the edge state, that is a macro state of the system. So part of the excitation doesn't couple and is dispersed towards the bulk of the system, but that is normal. There's not a perfect overlap between, as shown here, there is not a perfect overlap between waveguide 0 and the entire edge state.
So what does that mean, teleportation? That means from one edges to another, thanks to, I cannot have a picture of the physics that is at play. I don't know, anybody has a picture here? At
this point, there is no teleportation.
Yeah, but when you go to quantum teleportation means that, there should be some kind of state information that you get somewhere where you are acting somewhere else, right? So
yes.
Oh, it's projecting 1D.
So
1D system.
Topology does not enter the teleportation protocol itself, but it enters how we include topology in this protocol in the way that Alice and Bob obtain their entangled states that allow them to do the teleportation. This protocol exists before topology had some role in optics, but for this protocol to be performed, we need to have an entangled state between Alice and Bob.
Yeah, but what are Alice and Bob? They are part of the chain, or where are they in real life?
These?
Where do they are in space? Alice and Bob. They are sitting somewhere in.
Alice are far away. Alice is in Chile. Bob is here.
At the infinite of the chain. Or they don't.
Alice is in Chile, Bob is here.
Yeah.
And let's say that in the United States, they can generate two-mode squeeze states that are like perfect.
On your chain, and then they send it.
So in United States, they generate the states and they send them to Alice, that is in Chile, and Bob, that is here, via SSH waveguide arrays.
Okay, two states, split states that will send the split state generate here in this model.
Yeah, one SSH waveguide array goes towards Chile, the other one comes here, and we can perform a teleportation between ICN2 and Universidad de Chile.
So it's a SSH, so it's a 1D chain which you excite optically, and you, for some reason, because of topology, you create squeeze state that then they can flow away from the chain somehow, and then you will measure that property.
They don't flow away from the chain. You think of a one-dimensional chain, but it is constant along the solar axis along which light propagates. But if we look at the beginning, we look at the middle, we look at any point of the propagation, and we do a transverse cut, it is still an SSH chain.
Okay. Yeah, I will let Sergio, because we have time. You will be here for years, so I will get to the bottom of it. But now I cannot get a picture.
I have the same problem. I don't get a complete picture. So if I understand correctly, the UV term.
No.
So these UV terms actually determine the coupling that you have in consecutive elements in your chain, right?
Yes.
So and then you have a topology when you have a U term, which is the one on the first one, is smaller than the V one, right?
Yeah.
But if you're looking for a topology in a system, it's typically given by what happens in the middle, right?
Yeah.
Not how you really cut it. And what happens in the middle is basically the same, only you have a topology state when you have these islands a little bit isolated from the rest. So this, I don't quite follow. Why you say that this is topological?
Okay, that is not a debate that is starting here, because where the SSH actually does have topological protection or not is something that goes back a while. But what is a fact is what I have shown here, that the edge state, the SSH system does have some edge states. And the characteristics of these edge states, I show here the eigenvalue, but also the edge states have perfect sublattice polarization. So both of those characteristics are completely resilient to any symmetry-preserving form of disorder. Symmetry would be chiral symmetry. When introduced disorder that breaks chiral symmetry, these properties start to fluctuate. So that is a fact. Where we call that topological or not could be a philosophical debate. So if we say that this model is not topologically protected, we can say that this is protected by chiral symmetry of the system, and the conclusions work regardless. If we introduce any form of disorder that preserves chiral symmetry, we will preserve the phase of the squeezing. So it's a pragmatic point of view. I decided not to enter on the discussion on whether it's topological or not, but I would rather defend the conclusions here.
What would be the advantage of using the squeeze light state for quantum teleportation?
Okay.
Topological versus the normal entangled quantum state for teleportation.
Okay, so
the advantage.
Your question is on the advantage of squeeze states or the advantage of topology? Of topology, okay. Because for any
yeah, because we have the impression, sorry, Joaquin, we have the impression, this is a good question, this is a key question, that to some extent you generate entangled photons in a topological system, then somehow entanglement is more robust or something that this is what we no?
Yes, the whole point of teleportation is to preserve the quantum state that you have sent, yes, and avoid dissipation or interaction with strangers. So on the one hand, topology would, I imagine, add to the protected or the protection of that state. On the other hand, it will be difficult to read it at the other end. You see?
Yes.
I'm trying to find out the motivation for the work, because the quantum teleportation has been demonstrated over tens of kilometers.
Yes.
And so tell me, why, what is the advantage?
Okay. What we found here is a topological protection of the phase of squeezing. So if we're looking for any advantage of this system, we would have to look at phase-sensitive measurements or phase-sensitive implementations. For example, the teleportation protocol that, of course, I selected to do here. I was clicking the wrong button. The quantum teleportation here is phase-sensitive. So if something isn't phase-sensitive, there is no point of using this SSH lattice.
Yeah, can I just stop you a moment? Because what I'm also, I have the same kind of confusion, but it's very interesting. Similar confusion that, you know, quantum teleportation, as ICREA say, you create an entangled photon pairs, you separate those photons, and then you measure the correlation when they are far away, far in distance. Here it seems that the implementation, your waveguides, and the fact that you create entangled squeeze state in your waveguide that has some topology makes it much more, makes the entangled pair more robust to some extent, as long as it propagates in the media where it has been generated. So maybe that's a kind of confusion that we have, that it is like the implementation. Your topological quantum teleportation makes sense as long as we remain in the implementation material. So
yes,
that's correct. That's what.
Yes, yes, of course. The protection is valid as long as we're in the SSH system.
Multiple waveguides in the optical fiber, all identical, always the same.
Yeah. Yeah, but there is, they select teleportation, but you could think about something else. You could think about manipulating photons.
Any phase-sensitive implementation.
Yeah, kind of different type of implementation.
But yeah.
Anyway, I really like to encourage you guys, you and the people that also of your group, we read this paper because it's kind of interesting to have this new concept, right? All topological effects in the materials, or what you're doing try to design some kind of materials to create topological photons and then to interact with phonons and so on and so forth. So and waveguides and so on and so forth. So that would be nice that we have time to read the papers, and of course this is a theoretical study. So, but imagine that there is it is source of inspiration for an experimental design. That would be really interesting, I think. Yes, okay, so that would be like a homework for those who can dedicate some time. The paper is not 100 pages. I guess this paper is like 8 pages. Okay, and I would be very happy you come back to us at some point and just like informal discussion. Okay, well, we don't understand that, and we deep a bit that because it's like it's something a new territory for all of us somehow.
But let me
please answer.
Also have make the final remark to your question of how would this be useful. Well, it's only the SSH system. It's pretty much the fragilest topological phase, if it's topological, ever, and it's not going to be of much use under any scenario, the SSH system. Why do we work with the SSH system? Because you start from the basic. You start from 1D, the simplest model, and that is why this system, I think could be of higher promise, because the edge states of a two-dimensional system would be more robust. I mean, in the SSH system, if one of these waveguides has a defect, if one of these waveguides is written and there is some sort of accident, we're doomed. So the SSH system is never going to be of much use because of that. So that's why it was interesting to move towards two-dimensional systems. But
the last slide, what there is doing at the moment, looks to me like, you know, it's kind of a bad experiment with photons, but with waveguides. So I don't know if this has been inspired by experiment, or if there is no experiment that can connect or can.
This exists. This has been experimentally achieved.
Yeah, but what you propose here to make a kind of correlation of photons. Polarization measurement in a kind of implementation with waveguide, right?
Yeah.
So this has been made experimentally or never? On top of the system, yeah?
The optic Haldane system has, but it's some Michael Rechtsman, his laboratory in United States. They have made the system, view the propagation of edge states, and that's all I know about that. But about experimental detection of these things. So this. Taking advantage of those topological edge states for some sort of implementation, interference, and that has not been made, but it is experimentally factable from what I have read. It is realizable.
Okay. So yeah, anyway, that's really interesting, pretty interesting. You have more questions?
There's plenty of room for discussion. We would also, I think we would like to show you the experimental implementations that we are working on, because we are a little bit far away from this, but keywords: sources, coupling, transmission in waveguides, and detection of signals in the waveguide, and all topologically protected. I mean, this is at least our work. So how you launch, how you input things can be optically, electrical, etc. But there has to be a robustness signal that we can say, yes, it is protected. Now, by design, obviously, we have to go to well-defined materials, the interfaces of which fulfill the role of topologically protected interface states, chiral or not. Of course, chiral will be more exciting because I think we already have a design for that, but that would be great.
Okay, yeah, thanks, Livia. Okay,
thank you.
Yeah, that's very, very nice. So we have to read your papers. Yeah, thank you. Thank you for your first in-person talk. Very good.
Thanks you a lot. for your attention and for coming here.
Well, I'd just like to finish that. Will be primarily working on spin physics, transport physics. Yeah. But you know, the point is also that you know, we are like in a gray zone where photons, where entanglement, all these things is exciting us a lot. So we will see all the topics, but there is a track. There are tracks, but then there are some possibilities and this is what we want, to have a more open discussion and larger discussion, getting inspiration about this, you know, this type of exchanges. Okay, thanks for coming. It was very nice, and I guess for you.
Thank you very much for being here.
Bye-bye.